to this, I guess, new format for the quantum colloquium. So we are going to start with a tutorial about quantum chemistry by Brian O'Gorman, who is now a PhD student here at Berkeley. And yeah, so Brian, just turning it over to you.
Great. Yeah, thanks, Umesh. So this will be a very short introduction to quantum chemistry aimed at computer scientists. So my primary goal will be to convey the idea that the main problem of quantum chemistry is nothing more or less than a very special case of local Hamiltonian. And then I'll conclude by briefly discussing some classical approaches and their limitation. So the model of the physical world that is relevant to chemistry is that we have some nuclei in space, these point charges, surrounded by a cloud of electrons. And of course, the nuclei are at some level, quantum mechanical, but they are so much more massive than the electrons that it's a very good and common approximation, known as the Born-Oppenheimer approximation, to treat them as classical. So we'll just treat them as fixed points in space. But the electrons, on the other hand, we need to treat as quantum mechanical in order for our calculations to match what we see in the real world. Like there seem to be inherently quantum dynamics in these molecules. And so what we'll do is we'll fix the nuclei in space. We'll solve for the electronic ground state. And we'll do this for many different configurations of the nuclei. And if we do this over a range of configurations, we can start to sketch out this energy landscape as a function of the nuclear coordinates. And this allows us to do chemistry because molecules are just the local minima of this energy landscape. And if we understand this landscape, then we understand what molecules exist and how they turn into each other, how chemical reactions take place. And so in order to do chemistry, we need to sketch out this landscape. But really the hard part is just finding this electronic ground state at any particular point in the landscape. And so after this slide, I'll exclusively talk about that problem. We'll fix the nuclei and we'll try to find for the lowest energy state of the electrons. But two things to note about this problem is first that we can move this energy landscape up or down globally, and it doesn't change anything. So if somehow we had a method that was systematically but consistently wrong by some fixed additive amount, that would be fine. All that matters for chemistry is energy differences, not the absolute energies. And another thing to note is a comment on how precisely we need to solve this problem. So you'll often hear chemists talk about chemical accuracy. And sometimes they'll mean, they'll quantify that by referring to some absolute energy, like a millihartree or something like that. But what they really mean is that, we can solve the electronic ground state problem sufficiently precisely so that, if we solve it a bunch of times and sketch out an energy landscape, that this energy landscape, at least qualitatively, looks like it should. Its features, its local minima, its humps, match those of the real world. And if we understand, our computation of the energy landscape, then we understand, the chemical dynamics of the system. And another thing to note is that, we'll focus on the ground state problem, but sometimes chemists are also interested in, closely related problems like other properties of the ground states or even properties of low-level exciting states, low-energy excited states. And so we fix the nuclear coordinates and we ask, what is the lowest energy? And this energy function has two components. One is completely independent of the electronic state. So it's just the interaction of these positively charged nuclei interacting with each other. But because we're fixing the nuclei, this is a constant. And going forward, we'll just completely neglect it. It doesn't change with respect to the things that we're optimizing over. And what we really care about is, again, this lowest energy electronic state. And this expression on the bottom should not yet make sense. But over the next 10 to 15 minutes, I'll build up and return to this in a way that hopefully will make sense. So before talking about the Hamiltonian itself, I'd like to spend a little bit of time talking about just what I mean by the state of electrons, because there are some slight differences between the states of electrons and, say, the states of qubits. So things are quite simple if we just have a single electron. We have this wave function in real space. It's normalized. The square of its magnitude over some region of space gives the probability that an electron is in that space, that region. But this wave function is a continuum object. And we want to compute things. And so we need to discretize the system in some way. And the way that we do this is by choosing some finite basis of single particle orbitals in which we can at least approximately represent this state. And so once we've done that, we're approximating this wave function in real space, but on our computers, it just looks like a qubit, right? We have some n amplitudes that represent our wave function within this single particle basis. And but ultimately, we want to choose a good basis. We'll want to choose a basis function, set of basis functions that minimize what's called the basis set error, which is the difference in energy between the true ground state energy and the lowest energy of a state within the space spanned by our basis. And so things get a little more interesting when we move to 2 electrons. So again, we start with some wave function of 2 particles in real space. It's normalized. We discretize it in some way using some finite basis. And again, on our computers, this just looks like a pair of qubits. But this is where physics comes into play. These electrons are identical or indistinguishable, which means that the wave function needs to be symmetric or antisymmetric. And in particular, electrons are fermions, which means that the wave function needs to be antisymmetric. So operationally, this means that we need to restrict our attention to states that are -1 eigenvalues, -1 eigenvectors of the swap operator. And so instead of considering all states of these 2 qubits, we need to restrict our attention to this antisymmetrized state, which is much smaller. I mean, it's still combinatorially large, but it's not the full state of 2 qubits. And in particular, one implication of this antisymmetrization is what's called the Pauli exclusion principle. The idea that 2 fermions, 2 electrons, cannot occupy the same state. So for example, here, if P is equal to Q, these 2 things cancel out. And so the only non-trivial parts of this superposition are those where the electrons are in distinct states. And because of that, there's this alternative way of looking at the states of these 2 particles, where instead of saying, this electron is here and that electron is there, we look at the possible places that it can be, the possible states that it can be in, and we just say how many electrons are in those states. And because these are fermions, that number is just 0 or 1. And so in this occupation representation, also known as the Fock basis, we can represent our basis states by simply bit strings that say whether or not each orbital is occupied by an electron. And so for concreteness, suppose we had 2 electrons and 4 orbitals. We have these equivalent particle and occupation representations. And an arbitrary state of these 2 electrons in these 4 orbitals is spanned by these 6 states, rather than say the 16 states of 2 qubits. And of course, we want to treat systems that have many more than 2 electrons. And so what does this look like for an arbitrary number of electrons? So we start with what look like qubits, but now again we restrict our attention to the antisymmetric subspace, the -1 eigenspace of every pairwise swap operator. And again, we have these 2 different ways of representing states. So one is by sets of distinct orbitals and the anti-symmetric summation over them. And there's a way of writing this expression in the second to last line such that it literally is the determinant of a particular matrix. And so often we'll refer to this set of orbitals as a determinant, which has this alternative representation by a bit string that just says, where the 0 or 1 indicates which orbitals are in the determinant or not. And so those are ways of representing states. We also need to represent operators. And in the occupation basis, we do this by with what's called the annihilation and creation operators. So all these do is act on states with an electron in a particular orbital and remove it. So this is the annihilation operator. And the creation operator acts on a state without an electron in a particular orbital and puts one there. And these are elementary operators in the sense that an arbitrary operator on these states can be expressed as some combination of these, sort of in analogy with the Pauli operators for qubits. And there's a special combination of these called the number operator that just tells us whether or not there's an electron in a particular orbital. And so these are quantum operators. They do not commute. And in fact, certain pairs of them anti-commute. And the useful thing about these operators is that we've moved the anti-symmetrization from the being encoded in the state to being encoded in the operators. And so now we can start to talk about what is the Hamiltonian that we care about. So at least the part that depends on the electronic state has 3 components. One is the kinetic energy. These electrons are particles moving around in space, and there's an energy associated with that. And the other 2 parts are simply the Coulomb or electromagnetic interaction. So there's an interaction between the electrons and the nuclei. This Zi is just the charge of the nuclei. And these are oppositely charged particles, so this is contributes negative energy. And then there's the interaction of the electrons with themselves. And they're both positively charged, and so this is a repulsive interaction. They want to move away from each other. And so this is this captures at a high level the competing parts of the Hamiltonian. We have these centers of atoms in space. The electrons are attracted to them, but they're also repelled by each other. And so the true ground state tries to find this balance between being the electrons being near the nuclei and also away from each other. And so viewed as a formal computational problem, an instance of this Hamiltonian is specified by a few simple parameters: where the nuclei are and what their charges are, and the number of electrons. And that's it.
Could I ask which parts of these Hamiltonians commute and which parts don't commute with each other?
These 2 parts don't commute. Yeah.
Thanks.
I mean, this is so this is just this nabla is like a derivative operator. And so these parts are just diagonal in some continuum position basis, and the kinetic energy operator is not. Yeah. So I mean, like very, very informally, this is sort of like an X and Z situation. Yeah. I mean, it's position and momentum. Yeah. And that's actually maybe I shouldn't get too much into this, but in the some quantum algorithms, they exploit this. They'll like switch bases where part of the Hamiltonian is diagonal, and they'll rotate to a different basis in which the rest of it is diagonal. So yeah, so this is the Hamiltonian in the continuum, and again we discretize. We choose some basis of single electron orbitals, and within these orbitals, we get these coefficients of the Hamiltonian that are just these integrals over these physical energy operators. And so often chemists will treat these coefficients as the instance, as the problem they're trying to solve. But really, they're completely determined by a much smaller amount of information. And so in the particle representation, the particle basis, this electronic structure Hamiltonian literally is a two-local Hamiltonian. You know, we have these one local kinetic and external potential terms, and we have this two local electron-electron interaction. And one of the special things about the Hamiltonian in this representation is that all of these terms are identical. There's a single one local kinetic energy operator that acts identically on all of the qubits, sorry. And same for the external potential. And also, not only is there one that's repeated throughout, it has a lot of internal structure because its coefficients come from these integrals over particular operators. And so in this representation, the goal is to find the lowest energy antisymmetric state. And this may be a bit of a departure from traditional quantum Hamiltonian complexity, this restriction to antisymmetric states. But there's this alternative representation in the occupation basis where we no longer have to explicitly restrict our attention to the antisymmetric subspace because it's sort of baked into the formalism by construction. And so here, instead of having a two-local Hamiltonian, we have what's called one-body and two-body operators. So these one-body operators move, the terms of this one-body operator move a single electron from one place to another, and the two-body terms move a pair of electrons from a pair of orbitals to another pair of orbitals. And these coefficients are not completely arbitrary. As I showed a slide or two ago, they're completely determined by these integrals over these physical energy functions given the single particle orbitals. And so there's a lot of structure in these coefficients that can be exploited both by classical and quantum algorithms. And yet, despite how specific and special this local Hamiltonian is, still it's QMA hard. And I'll point you to an archive that my collaborators and I just put on the archive that goes into the details of what exactly I mean by this statement. And so this is about as much as I'll say about the Hamiltonian. And now we can start to talk about the how to solve it and the difficulties therein.
So can I ask you something? Yeah. So the Hamiltonian in this formalism is four local, right? In this latter one.
Yeah. So strictly speaking, this is like a quartic polynomial, but it's just you need to the important thing is so all of these physical Hamiltonians are number preserving. They have the terms have an equal number of creation and annihilation operators, right? Because this is a thing that is physically preserved in the system. Particles don't just appear out of nowhere or disappear. And so really there are four things here, but what really matters is that there's two of each. And so my sense is that you should really think of this as a two local operator. It's just that in this representation, that corresponds to having four things and two of each type.
So are these coefficients easy to compute, the HPQ and HPQ? So on?
Yeah, so they're easy to compute. Well, actually, so that depends on the choice of the orbitals. So these are the coefficients. These are the things that need to be computed. And this is why chemists often choose Gaussian basis sets. Because if these orbitals are Gaussians, then these things are easier to compute. And for other choices of orbitals, they are less easy to compute. And here, for a certain non-Gaussian choice of orbitals, they may be not hard to compute in the sense that we could do it polynomially, but there may, in certain cases, be like thousands of these. And so, easy and hardness in that case is, a matter of degrees of polynomials and not necessarily polynomial versus exponential. But yeah, and then there's a trade-off between storing it and computing it on the fly. This is a question both in classical and quantum computation, and these really large-scale implementations balance this in some way, depending on the resources and the particular system.
Okay, so in your QMA hardness result, you don't have to feed this HPQ as input. Like you can probably.
Yeah, so it's basically you specify the orbitals and then those imply the coefficients, and that's actually the progress that we made over previous work. So it was known that if you have a generic Hamiltonian that looks like this, and you can just arbitrarily set the coefficients. It was previously known that that was QMA hard, but what we showed is that if you just specify the orbitals and use the coefficients implied by those orbitals, then that is QMA hard, without a magnetic field that a previous construction used.
There's a question on the chat. Do you want to take it now?
Sure. Yeah.
You can see it, yeah.
Maybe we should keep going because we have only 8 minutes. So I don't know if you want to, how much time you have, Brian?
Yeah. So maybe a few more minutes. So yeah, let me just quickly answer those two questions. They should be simple. So we don't, I've stopped talking about the nuclear interactions because they're a constant. So we need to add them in when we're comparing different nuclear configurations. But for a fixed nuclear configuration, when we're optimizing over the electronic state, we don't need to always consider it and add it back in. And then the other thing is spin. So one thing I have not mentioned anything about is that electrons are fermions because they're spin half. And so whenever I talk about this orbital basis, they come in pairs where there's a spatial component and a spin up and a spin down component. So let me keep going. Classical approaches. Should be no surprise that this quantum Hamiltonian, you can have very entangled ground states that may be hard to represent on a classical computer, let alone find. And so one common approach is to, instead of optimizing over all electronic states, optimize over a smaller class of states that we can efficiently represent and manipulate. And in particular, the Hartree-Fock state is the best so-called single determinant. So we pick some set of orthogonal, distinct, single particle orbitals, and the Hartree-Fock state is the best one of those. It's the anti-symmetrized product of these orbitals. And so one way of thinking about Hartree-Fock is that it's sort of fermionic analog of matrix product states and serves many of the same roles. And to find this Hartree-Fock state, we iteratively solve the set of coupled equations that consider the effects of the electrons on each other, but only in some average way. And so the end result of these Hartree-Fock calculations is a sort of mean field approximation. And for many systems of interest, this gets us very far. It gets us 90% of the way there. But we often need to go further and need a more precise answer. And so there's a family of methods called configuration interaction that looks at not just the Hartree-Fock states, but states that are nearby it in some sense. So without loss of generality, we can write the Hartree-Fock states in this simple way. And then we can start asking about, we can optimize over states that are near the Hartree-Fock state. So we have single excitations, doubles, triples, and so on. These are like the number of hops away. And we can keep going. And if we keep going and place no restriction on the distance from the Hartree-Fock states in a way, we get to what's called full configuration interaction, or full CI, which is exact in the basis set. And it's sort of like the gold standard of these types of calculations. It allows us to benchmark and verify other approximation methods, but it's exponential. And so it quickly becomes infeasible for even moderately sized systems. And there are other ways of going beyond Hartree-Fock, different ways of choosing the limited number of determinants to optimize over. And then the last thing I'll talk about is so-called density functional theory, or DFT. And the idea here is that instead of thinking directly in terms of the wave function, we'll consider the electron density, which is just tells us, how many fractional electrons are at each point in space. And the basis of DFT is that there exists a so-called universal functional that takes in this electron density and tells us the expectation value of the Hamiltonian under the wave function that electron density corresponds to. And this is universal in the sense that this TNU, this kinetic energy operator, and the electron-electron interaction operator are instance independent. They exist for just whenever we have electrons in space, these operators are there. And then the instance specific part, this external potential, that's easy to calculate given the electron density. It's just a simple integral. And so this is very nice in theory, but this proof that the universal functional exists is non-constructive. And there's a sense in which it's provably hard to even compute this functional. And so in practice, what people do is try to compute approximations to this functional. And sometimes they work great, and sometimes they don't. And so to conclude, like I said, the point I was trying to convey is that the main problem of quantum chemistry is just a particular type of electronic structure Hamiltonian. And at least classically, it's very hard to solve. And in the worst case, it may be hard for quantum computers as well. But there's hope and expectation that for at least a lot of the instances that we care about, quantum computers can help us go well beyond what we can do classically. And in a few minutes, Matthias will tell us, how and why that's the case.
Great, thanks, Brian. Quick question: can you address this? Say a little bit about what it means to compute something to chemical accuracy.
Yeah. So there's sort of like two answers. One is that it's often just like it'll be like 1 millihartree. It's like these are these Hamiltonians in physical units, and it'll just be you need to be within this particular amount. And sometimes it's just a matter of doing a little bit better than the last calculation. But really what it means is that the chemistry, what is the dynamics of the system really depend on this energy landscape. And so chemical accuracy just means that the energy landscape looks like it should. If a certain bond exists, then it's captured by the energy landscape. And so there are examples where the easiest chemical systems to think about are just these diatomic molecules, where the only configuration parameter is a single internuclear distance. And the question is like, do these two atoms bond or not? And so in that case, chemical accuracy means that if there's a bond, then we see it, and if there's not a bond, we don't see it. And then that's a simple example. There are much larger molecules are much more complicated, but morally it's do our answers qualitatively match empirical data? That's what chemical accuracy means. And then like translating that into like inverse Pauli or something like that, it's a little hard because chemists typically don't think in terms of infinite family of instances. It's like here's a protein or here's an enzyme. I need this amount of accuracy. And so there's no sense of real scaling with system size or something like that because there's only one system.
I think we are now at the time for to transition to the colloquium. So let's see if if Matthias is here, Brian, could you stop sharing your screen?
Oh, yeah, of course.